All right, so we want to go through a sample type of a quiz. And okay, so what do we have? We have our soil profile. We have sand, clay, sand, and everything is in meters and kilopascals, kilonewtons per cubic meter. Here are the soil or the densities for the sand, and this is the clay, and this is the sand down below. And we have tests at 4 meters depth, 6 meters depth, 8 meters depth, 10 meters depth, and 12 meters depth. So we have samples A, B, C, D, and E. And so this is the test for sample A, sample B, sample C, sample D, sample E. So we have all of these tests, and our goal is the same as what we've been doing previously, is to find C prime and Phi prime in the clay, to find SU and tau FF drained. So find SU and tau FF drained. So SU is undrained shear strength, tau FF drained. Depth of 6 meters in situ. All of the tests shown here are direct shear, and if there's no U excess shown, then that means it was not measured. And somehow what's not in here is we want to find SU over sigma prime I, versus OCR. So along the way, in other words, to get this, we have to get that. So implicit in this is that we have to plot up SU over sigma prime I. And in other words, we've been asked to complete the table on the next page, which I'll show you. What you should note about this is, okay, so I'm looking at, look at the first test. Oh, fast shear, meaning it's an undrained test, and we have measured excess pore pressure. And it's in the clay. So that's in the clay. Undrained test, measured excess pore pressure. B, it's a drain test. Excess pore pressure is 0, so it's not measured. C, it's an undrained test, but fast shear, but notice we did not measure the excess pore pressure. For D, again, undrained test, but no excess pore pressure measured in the clay. And then E is in the sand, and of course it's a drain test, and there's no excess pore pressure. So that's what we note. And so you're going to have to go back and forth on this. We need to find Phi prime in the sand, if I didn't say that. So we're going to take, here we're plotting tau versus gamma, shear stress versus shear strain. And, we have the sigma V given that we applied in the test, and then what we're picking off is the peaks, all of these peaks here. We need to use those, and then where applicable, we need to use the excess pore pressure. It looks like that's the only one that has any excess pore pressure. So what you want to do is you want to complete this table. So you'll have to go back and forth on the video. You can copy down this table yourself or get one from an example problem I've given or something, however you want to do it. But so we have, there actually should be one more point shown here, and that would be E needs to be put in there. So what you should do is you should, make these table headings and make this. So create this table, fill it out, and then what you want to do is to compute your phi prime in the sand, your C prime and phi prime in the clay, and then plot up your SU over sigma prime I versus OCR there, and then the in situ values there. So pause the video and do this calculation. Fill in this table. Okay, I'm assuming you have done this, and let's look at the answers. So the first thing to find is sigma prime in situ. So I'm not going to go through that. We've done this many times. You simply use the unit weights and the depths and come up with the, and subtracting off the pore pressure and coming up with the sigma prime in situ. So that's find this from the soil profile. Okay, and then sigma prime P in situ. Well, what's sigma prime P in situ? I guess I didn't point out that the OCR is 1.4. So OCR is given to be 1.4, and so we take this column, multiply it by 1.4, we get that column. Then the sigma prime I from the sample, where does that come from? For the sample, well, we've established that comes from these numbers here. Those are the sigma prime I's for the sample. So we just list them here. Then what is our sigma prime P of the sample? Well, okay, we're going to compare this column to this column and take the greater of those two. So what do? 120 versus 67.8. The greater is 120. 90.7 versus 60 is 90.7 is the greater. 113.7 versus 100, 113.7 is the greater. 136.6 versus 100, 136.6 is the greater. So this, in other words, what we figured out here is the greatest stress the sample has ever felt. And you're determining whether it was greater in the ground or greater at the beginning of the test. So the biggest of those two. Then once we've determined the sigma prime P of the sample and the sigma prime I of the sample, I take sigma prime P divided by sigma prime I, that gives me the OCR. So divide those two out and I get the OCR of the sample. Where the tau FF, where does that come from? That is given from the peaks, the peak tau. You don't have to figure it out. So you're taking these values here, and those are the tau FFs. Then we have to look at the test. I've already gone through it. Is it undrained? Drained. Undrained, undrained, drained. Those are the tests, depending on whether they're slow or fast. And if it's undrained, then my tau FF is my SU. If they're not undrained, then it's not SU. Then I can't get my SU. So I'm getting SU, the undrained shear strength, from that, and then I simply take the SU over the sigma prime I of the sample, do that division, that gives me that column. And then the sigma prime FF. Well, sigma prime FF, for the drain tests, sigma prime FF, because there is no excess pore pressure, are the same. So that's the same, that's the same. For the drained for these drained tests. For the undrained tests, well, to get the sigma prime FF, I have to measure the excess pore pressure. There was only one test where I measured the excess pore pressure. That was the first one. We measured the excess pore pressure there. And at failure for that first test, we had an excess pore pressure of 5. So that means I take the 120 minus the 5, that gives me 115. So in other words, my sigma prime at failure is reduced by the excess pore pressure created. So, okay, so now I have the sigma prime FF, I have the tau FF. And what I can do with that is, well, first I'm looking in the clay here. So these are the only tests in the clay. And of those tests in the clay, I only have 2. I've got that one, and I've got that one. So it's 115/30 and 60/20 are my points. 115/30, 60/20. I'm not going to go through it. You can draw that line. You can write the equation for that line. There it is. The intercept gives me my C prime. The arctangent of the slope gives me my phi prime. Okay, so I've been able to get the clay drained failure envelope. Now I want to work with the sand. Well, that's test E. And so what's my point? I've got 15, 14. So 15, 14, plot the point there. I get the phi prime is the arctangent of the angle. And, okay. So now I want to get my sigma, SU over sigma prime I versus OCR. And I'm going to plot those points, or at least some of those points. So what do I have? Now, what I have to recognize is that my in situ OCR is 1.4. That was given. So there's my in situ OCR is 1.4. So just what we can see is I'm interested in OCR, if I have an OCR close to 1.4, that's going to be good for me, but no matter, I'm going to plot these points. So I have, so I only have I have 3 points that I can plot here. And so let's take a look at that. So I have 1.25. I guess that didn't quite get plotted, but let's do it right now. So I can put down one is over here, so that point would be 1, 0 point. Oops, it's not drawn very well to scale, so it'd be down in here somewhere. So 1, 0.25 for that point right there. And then the others are shown as 1.14, 0.48 is given, 1.37, 0.65. So those are all shown there. And so 1.37 is pretty close to 1.4. So I'm not interested in this region over here, so I'm not going to write the equation of the line there. In other words, this is, I haven't drawn it, well, it looks like it, excuse me, it's a completely straight line, but it's not necessarily a completely straight line, so usually we draw a little bit at a time here. And, but 1.37 is so close to 1.4, I want this line right there. So I take these 2 points and I draw a straight line between them, And I'm not going to go through it. I would do y equals mx plus b. For those 2 points, I get y equals mx plus b. And that's in the region of the in situ OCR. So that's what I want. So I'm going to use this expression to help me get the SU over sigma prime I in situ. Well, it's going to be pretty close to the 0.65, but I'm going to, for x, what do I put in? X is the OCR, so I put in the OCR of 1.4, so there's my OCR of 1.4 for that expression. I get 0.673 for my SU over sigma prime I in situ, and then I get the sigma prime at the point of interest in situ, 64.8. Well, it just so happens we have already calculated that value by luck, because sample B is at the depth that we were interested in. In other words, the depth we were asked for was, we were asked for the depth of 6 meters. Well, point B is at 6 meters. So we got a little bit lucky there. We don't have to do another calculation. So I put in that 64.8. That means that what? I just do, to get my SU at the point of interest, I just take the in situ value, multiply it times the 0.673, and I get my SU at my point of interest, 43.6. Okay, so then the last thing we need to calculate is, what is my drained tau FF at the point of interest? Well, in that case, now I'm going to use my drained envelope here, and I'm going to use, again, my in situ, because it's at 6 meters that I wanted it, the 64.8, so I'm going to use that for my sigma prime, and that means that I simply take that x value is going to be 64.8, because x is sigma prime. I put it in, I get 20.9 kilopascals. That is how we do this kind of problem. And I will stop.